Sim hydraulics is used in a number of industries, including the automotive, aerospace and defense, and medical industries. We'll look at a couple of different applications. The first is a fluid power system. We have a backhoe that is modeled with multiple hydraulic cylinders. The hydraulic system consists of many components, including a pump that supplies pressure to all of the actuation systems, valves controlling those actuators, and a control system that tracks a reference position. Sim hydraulics is used to select the hydraulic components, for example to size the actuators that will be used, to test system integration, seeing what happens when we combine the hydraulic system with a three-dimensional mechanical system, and to design the control system for this backhoe, including hardware-in-the-loop testing. I'll now switch over to the model so that you can see how this is done. Here is the model that we're working with. We have a model of a backhoe that has 3 hydraulic actuators. The pressure to these hydraulic actuators is controlled by a control system, which attempts to track a reference angle. When we run the simulation, we can see how the backhoe performs. The three-dimensional animation is provided using sim mechanics, and we can see how the bucket and the arm will move. On this scope, we can see how well the control system tracks the reference angle here in pink. Going into the model, we can see how sim hydraulics is used. Sim hydraulics models the hydraulic network that controls the actuators. We can see a pump, a pressure relief valve, and the physical connections that connect the hydraulic components together. The hydraulic components are drawn from the Simulink library browser beneath Sim Hydraulics. You can see some of the libraries here. The hydraulic actuators themselves are made up of a directional valve and a hydraulic cylinder. Components in Sim Hydraulics provide multiple parameterization options. This makes it easy for you to assign realistic values for your hydraulic components. You can also use MATLAB variables to parameterize your components, so that you can perform parameter sweeps to size the components. Sim Hydraulics provides a library of hydraulic fluids. You can select the fluid and assign relevant parameter values. You can also add your own fluids to the database. Connecting your Sim Hydraulics network to a three-dimensional mechanical model in Sim Mechanics enables you to test your model with a realistic load. And by combining that with a control system, you can test your entire system, optimizing system performance. The entire model can be converted to C code, enabling you to use hardware-in-the-loop testing or deploy your model to other environments. Sim hydraulics can be used to model fuel supply systems. Here we have a system with fuel tanks, valves, pumps, and pipelines. This example fuel system, modeled in Sim Hydraulics, looks like this. In this model, the pressure drop in the fuel lines depends on the elevation. Directional and check valves are used to control the flow of fluid through the system. Sim Hydraulics is used to evaluate the architecture of this fuel supply system, design the control system, and test this system under different conditions and scenarios. I'll now switch over to the model so you can see how this is done. Here is the model of our fuel supply system. We have a tank in each wing of a plane, as well as a central tank. These tanks are connected by fuel lines, and the pressure drop in these fuel lines depends upon the elevation at each end of the pipe. We control that elevation using these signals. If we look at the tanks themselves, we see we have a variable head tank, which is connected to a tank valve that controls the flow out of the tank. Centrifugal pumps are used in parallel to draw fuel from the tank, and these check valves are used to prevent the flow of fuel back into the tank. This tank system is also replicated on the other wing. The central tank has valves that connect it to each of the tanks in the wings, and there is a very simple control system that controls when these valves are open or closed. When we run the simulation, we can see how the system performs. These scopes show the level of fuel in the tanks, as well as the pressure at each tank. This simulation, which is about 3,000 seconds, shows how fuel is drawn from the tanks in the right and left wing, and the level of fuel in the central tank. We can see that as the plane banks, the pressure increases on one tank and decreases on the other. This results in a fuel imbalance in the plane. Using MATLAB scripts, we can run a series of tests. Here you can see we've configured a set of tests with the varying elevation of the plane or bank angle of the plane, and then we are causing different pump failures with these signals. Using this MATLAB script, we can run these tests in series and save the results to the MATLAB workspace. we can see that as the different pumps fail, the fuel balance on the plane varies. This plot shows how the system performed for the 3 scenarios that we tested. We can see that using MATLAB scripts, we can automatically evaluate how this system and the controller performs under different flight scenarios.